Alright, so in the previous two videos I was considering a pretty simple biological system where you have some protein X, and here the square brackets are just denoting the concentration of X. So X has some initial concentration, and then over time a reaction occurs that degrades X, and this reaction has a rate beta. So this was the simple system that we were considering in the previous two examples, and we showed that this could be modeled by a simple differential equation that looks like this. In this video I want to sort of take this to the next level. So instead of just having a protein that is degrading and going to zero, I'm going to have a protein that has two possible states. So the first state is its regular sort of, it gets made, and this, we'll just call this the inactive state. This is the inactive state, and we have a second state, which is, which we will denote by the concentration of X, and we'll just put a little star to denote that this is the active form of the protein. And so, again, this is the concentration of the active state. Okay, so when, so similar to the previous example, we're going to have a inactivation rate beta, which is similar to the degradation rate, you can think of it. So, except now when the protein gets inactive, it just goes from X star back to X, but it can still be activated, and it can be activated at a rate alpha. And we will just assume, in this case, that alpha and beta are just constants. Okay, so now the question is, why are we interested in this kind of a system versus the first system? Well, the first system's kind of boring. It just doesn't tell us anything too interesting, just that if you have a protein and it's degrading, over time it degrades and asymptotically approaches zero. In this case, now we have a single protein that can switch between two possible states. And for computational neuroscience, this is actually extremely important, because this is essentially how ion channels are often modeled. And you can think of an ion channel as having two states. It's inactive state when the channel is closed and it's not passing any ionic current, and its active state when the channel is open and it is passing current. And it can switch between these two states by two rate constants, alpha and beta. And right now we're just going to assume alpha and beta are constant, but I will note in the future, they're not always going to be constant. In particular, for ion channels, they are going to be voltage-dependent functions. We're just going to think simply, just take a simple case where alpha and beta are constant. Okay, so how are we going to model this system? Well, I'll just write it quickly one more time. Sorry, that's an alpha, and the backwards rate is a beta, and we have the active state of the protein here. Okay, so as before, so I'm going to write a rate equation for the formation of this active protein. And we're going to, I'll start with something that's familiar to you. You have negative beta X star. So if alpha was equal to 0, this would be the equation that defines the change in concentration of active protein. And this is exactly exponential decay, what we had before. So this is, if you look at this, this is, you assume alpha is 0. This is exactly what we talked about in the previous two lectures, and that's why I wanted to start there and then move up to this example. If alpha is not equal to 0, then we have an additional term. Draw that a little bit better. We have alpha times X. And the intuition here is the same as before. So remember, for a higher level of X star, there will be a greater degradation rate. So the degradation rate is negatively proportional to the amount of active protein. And likewise, the creation of active protein is rather than inversely proportional, it's directly proportional to the actual, to the concentration of inactivated protein. And this basic idea should make sense to you. If you have more reactants, you can think of this as reactants. If you have more reactants, that will drive the forward rate of the reaction. And if you have more products, that will sort of drive the reverse reaction. So if you've taken any chemistry courses, these terms and the sign conventions for beta and alpha should make sense to you. Okay, so I'm going to take this equation. So you'll note now that this equation has two variables, whereas before we just had one variable x. So we have the concentration of X star and the concentration of X. And I'm going to simplify this equation by dividing both sides by the total amount of protein X, regardless of its state. So dividing both sides by concentration of x plus the concentration of x star. And when I do this, I'm going to get d x star over x plus x star. So I'm getting the change of that sort of weird variable minus, or actually I'm going to switch, I'm going to say alpha, just switch these two terms. Alpha over x plus x star minus beta x star over x plus x star. And if you look at this a little bit, you'll see that there's a easy way to simplify this equation. And I'll just write it down now, but I will show you how this is the case. So I'm going to put in x for this x star over x plus x star. So that's equal to alpha. Now this isn't quite x, this is x over x plus x star, and that's equal to 1 minus x minus beta x. Okay, so this here is what I'm defining to be x. And you can see that this here, this term, if you look at it long enough, this is equal to 1 minus x. So that's what that is. So now you're probably asking, why did I make that change of variables? Why am I defining x in this way? So this is the equation we got at the end of the day. And we're defining x to be the concentration of activated protein over the total amount of protein in its active or inactive form. Or rather, I should say the total concentration of protein, regardless of its form. So this you can think of as the proportion, or you can't, it is the proportion, and you should think of it as the proportion of active protein. So if it's a proportion, it's living on the interval 0 to 1. So you can't have a negative concentration of any of these. You can't have a negative concentration of any protein. So that imposes this first lower limit. The upper limit comes from the fact that x is maximized when the concentration of x equals 0, and then you just get x star over x star, and that equals 1. So, so this is a simple equation where we were able to take a system in which you had two variables, x and x star. So you have two dynamical variables, but we just wanted to simplify it down into this form here with this change of variables. So in the next video, I'm going to talk about what kind of dynamics can we expect from this more complicated system. Okay, thanks.